Hello and welcome to our discussion of vector fields on manifolds. Now, towards the end of last lecture, I had stated this result that if you have a compact manifold, then any vector field on the manifold is complete. And before that, I defined what a complete vector field means. It's just that the condition that all integral curves of x are defined on R. Now, let me briefly outline the proof of this theorem. Oops, so let's take this and then this outline of proof. First, let us note that we have the notion of given, so let's consider this differential, the equation for an integral curve. If sigma is an integral curve, of x starting at P then by definition sigma satisfies the following equation, which is sigma prime t equals x at sigma t and sigma 0 equals p. Right. So, and here sigma will be defined on some interval containing 0. Now, what one can do is let I be the union of all intervals containing 0 on which there is a solution to star. Star is this system, this initial value problem. So the point here is that I've taken a specific, when I wrote this, I took a specific integral curve defined on some interval, but it's conceivable that there's a larger interval on which there is a solution to this star problem. So what we do is we take the union of all intervals on which there is a solution to this. And when we do that, by uniqueness, we know that if there are two intervals on which there is a two intervals containing 0, then on which there are solutions to star, then on the common intersection interval, these two solutions must agree. This enables us to talk about the maximal interval, which I have called I. I is the maximal interval on which star has a solution, i.e. maximal in the following sense, i.e. if J is another interval, J is an interval on which star has a solution, and J contains I, then j equals I. So you can't make go past the interval I and still hope to get a solution. Now the point is that I made a remark about uniqueness of solutions on common intervals and so on. That is used to say that on I itself there is a solution. The way I was defined was that I is a union of intervals on which there is a solution, but we didn't assume that there is a solution on I. But the fact that on each member of the union there is a solution enables us to, and they agree on the common on the intersection portion, enables us to define a solution on I. So let me just say that remark if let I equal to union over some index at alpha j alpha, and j alpha are solution intervals on which there is a solution. We have a solution on I. So how do we define the solution? Well, we just take I have to just specify what the value of the solution is at any point. Let t belongs to I, then t will belong to some j alpha for some alpha. Then what I do is I just use the solution on j alpha to define. So we have a solution. So here let me denote the solution by sigma. Sigma from I to M. We have a solution sigma from I to M, and that's defined as follows. So let t belong to I, and then t belongs to some j alpha. If sigma alpha is the solution on j alpha, then we define this sigma t to be sigma alpha t. So here what can happen is that I took a point t in I, then I said that this t belongs to j alpha. Well, it can happen, and then I use the solution sigma alpha on j alpha to define this sigma t. Now it can happen that this t can, if t belongs to j beta for some other index beta, then this is actually what one would like to claim is that this definition is well defined. In other words, there is no ambiguity in writing it like this, and that happens because if this is well defined, if t also happen to belong to j beta, then on the common, so then t would belong to j beta intersection j alpha, and we know that, but uniqueness tells us that sigma alpha equal to sigma beta on j beta intersection j alpha. Hence, you get I might as well put this sigma t equal to sigma alpha t or sigma beta t. So even when we take a union of intervals on which there is a solution, on the union itself the solution is defined. Right. So once one has that, one has a maximal interval, maximal in the sense there's no larger interval on which there is a solution. So one would like to claim, so what one is aiming for, completeness of X is equivalent to saying that the maximal interval I equal to the full real line minus infinity to infinity. So this is the what one is aiming for. So now so far, I mean, compactness of X did not play a role. All this remarks that I made about was just to define the maximal interval. Now coming to compactness, suppose now we have fixed some point P, and suppose I, in fact I should put IP here for all P in M. So IP is this, so let's use IP, let IP and IP. So suppose IP equal to, now if it's not the full real line, two things can happen. Either the right endpoint is finite or the left endpoint is finite. So let's further assume the right endpoint is finite. So suppose IP is equal to AB with B less than infinity for some P, for some P in M. So in other words, the integral curve starting at this specific P cannot be defined on the full real line. You have to stop at some positive, it goes all the way up to some positive time, finite positive time, which I have called B. Now what I would like to say is that the idea of the proof is quite simple. So you just want to say that, and we already have a solution here, let sigma be the solution to star. Now idea of the proof is just to, this IP is an open interval. What I would like to do is that I would like to define sigma all the way up to B. So in other words, I want to define sigma of B, and in a smooth way. And once I do that, then I can again start this solution to the, find a solution to the differential equation, to the integral curve problem, starting at this point B. So and then combine the two solutions and get a new solution which is defined on a larger interval. So let me just make this, elaborate on this. It is enough to define sigma of B so that So this map, now that I've included this, is, in fact, it's enough to just say that this is actually continuous. So suppose I know this claim. So this is a claim. It is that it's enough to do this, because let's see why this claim would imply the main result. So we are supposed to get a contradiction since we assumed that b is less than infinity. So the contradiction arises as follows. It's enough to define this. So that's a proof of claim. If not, yeah, right. So if suppose we have such a sigma, let gamma be the integral curve of x starting at b. So this is our manifold. So the point P was here, so I taken the sigma, and sigma B is some point. Now what I'm looking at, gamma is the integral curve which starts at, not at B, but rather sigma B. Let's give it some name, at Q equal to sigma B. So this is Q, and this part is gamma, this part is sigma. Now, as one can expect, after all, this is an integral curve, so it's tangent to the vector field throughout, and one can expect that the sigma and gamma combine, patch up smoothly to give an integral curve starting at P. So the claim is that, so first of all, let's denote the interval. So gamma is defined on some interval minus epsilon, and it goes to the manifold, and by assumption gamma prime t equal to x at gamma t, and gamma 0 equals sigma of b. Then so what we can, once we have this gamma, I would like to say that I get this sigma combined with gamma. I'll say exactly what combined means. Actually gives a smooth integral curve. Let define, so define alpha from a curve start on the interval a to b plus epsilon and to m by alpha of t is just sigma of t for t less than b greater than a, and then alpha of t equals gamma of t minus b if t is greater than or equal to b less than b plus epsilon. Now I would like to claim that alpha is actually an integral curve of x, and note that alpha actually starts at, note that since the alpha 0 is well, as long as t is less than b, alpha is just sigma, so this is same as sigma 0 is p, and also alpha is continuous everywhere. The only issue is at b, but as we have assumed that as t goes to b, sigma t goes to a specific number, which is a specific point, which we have called sigma b. I mean, we have defined sigma b like that. So The only thing which, yeah, I would like to claim that alpha is actually an integral curve. Alpha is an integral curve of x. As long as if t is in this open interval, there is no issue. Then alpha is the same as sigma, which is an integral curve. Then it is clear. And similarly, if t is strictly greater than b and less than b plus epsilon as well, then again it is clear. So the only issue is what happens at, oh, by the way, notice that change the parameter by this constant, this t minus b does not change anything, because if I take the derivative of this, gamma prime t minus b is supposed to be, well, x at gamma of t minus b. So this is alpha prime t, and this is x of alpha of t. So for even in this interval, it's fine. The only issue is at t equals b. So potentially one problem can arise. This sigma, this gamma is actually defined. So if this is my point q, gamma, and this is gamma. Gamma is an integral curve, so therefore a smooth curve which goes both to the left of q and right of q. I mean, left of defined on left of 0 and right of 0. So that's okay. But we have on the left, when t is less than b, we are actually not using gamma, we are using sigma. So sigma is coming here. So it can be, it's the smoothness at q is not entirely clear. So that is the only thing one has to check, that it's actually smooth if alpha is smooth at t equals b, then alpha prime t exists, and I can just use the right hand side for that. So alpha prime t equal to gamma prime t equal to, well, it's actually gamma of t minus, gamma prime of t minus b. And just like what I wrote here, I mean, so I don't have to repeat this. In fact, the same calculations as in this brackets applies. Then is an integral curve on a to b plus epsilon, because the tangent vector at q, I can just use either the right curve or the left curve. Either sigma or gamma can be used to define the tangent vector, to calculate the tangent vector at t equals b. So in both cases, I'll get what I want. So the smoothness is the only issue. So how do we see that this is smooth? Now, before I, incidentally, this I'll not address this. Instead, this this part, the proof of the claim, is actually again does not use compactness as such. I've already assumed that sigma is it's enough to define sigma b, so that this is continuous. I've already assumed this. Once we have that, we can do all this. But The issue is, so here it does not require compactness of M. So where compactness does play a role is in proving that one can define sigma B. If M is compact, then we can define sigma B so that sigma from A to B is continuous. And in fact, one can do something more. Actually, one can make it differentiable from the left. But let's just see where compactness has a role to play. What we can do is let Tn be a sequence going to B. Now we consider sigma Tn. This has since M is compact, now this is just a subset of the manifold. Since M is compact, a subsequence of sigma Tn converges to some Q in M. Define sigma B to be this Q. Well, this is how one can start this way, but it's not at all clear that this way of defining sigma B will actually is well defined. I mean, for instance, that a different subsequence might converge to some other point. Moreover, if I start with a different sequence going to B, I might end up with completely different points and so on. So one has to show that just this choosing one subsequence is good enough, and in fact you can define Q, just catch hold of Q by just using one. And the reason is, it's just one notices that recall the classical if setting. If f from AB to R is a continuous function, actually what I need is not just continuous, uniformly continuous function. Uniformly continuous function then f extends to a continuous function on AB. This is the basic simple idea behind this, why this works. So what one can do is claim that that sigma from AB to M is uniformly continuous. Well, to talk about uniform continuity, one has to put a metric, a distance function, regard M as a metric space, and then do the calculations. The thing is that, why would we expect that it's uniformly continuous? And Again, go back to the one variable calculus setting. So here, what the small result that I wrote here, this is implied, this condition, rather note that if f from AB to R is differentiable, and note that f and f prime is bounded on AB, then f from AB to R is uniformly continuous. So in short, if we have a derivative bound, then we can ensure uniform continuity on the open interval, and that will enable us to extend the function all the way till the endpoints. That's essentially the idea. Even here, the sigma is, after all, the derivative of sigma is just given by the value of the vector field at that point. Now, the fact that M is compact again will help us here to say that the derivative in some sense is bounded. Now, to talk about derivative being bounded, derivative is of the sigma is after all a tangent vector, and to talk about its normal, one would need a what is called a Romanian metric, but there are ways around that. You don't actually need a Romanian metric. You can still, by working in local charts, one can get around that, but I won't go into details. But essentially the idea is that the derivative is the vector field, and the vector field on the whole manifold, since the manifold is compact, is the vector field is in some sense a bounded quantity, and that some sense one has the option of using metric, Romanian metric, or a local chart, and then use that to prove this and extend sigma all the way till the end point. And then next thing, so there are a couple of things left unsaid which I have not proved here, which is this here, the fact that the derivative, how to make sense of this bounded derivative, and how to prove that sigma actually extends. And this is this part uses compactness crucially. And then once we have this, then we have to show that this. So here actually this process gives not only that is continuous, is smooth, is continuous and smooth from the left at t equals b. So sigma b is continuous and smooth from the left. All right, so we'll stop here and we'll resume our discussion of vector fields in the next lecture. Thank you.